Our next speaker, Jojo, lives in Canberra with her one-eyed cat and another human. Thank you, Jojo.
Kia ora tātou. Yeah, I'm Jojo. I'm from iceLab, I work there. I'm the token Kiwi there. It's an Australian design studio. I'm a developer and I really love making apps for the web with Ruby and JavaScript. So I'm here to talk to you today about rom-rb. But at iceLab, we're a team of designers and developers who love solving hard problems. And over the last 2 years, we've been experimenting with and contributing to a new approach to building web apps in Ruby. We were motivated by a feeling that responsibilities kind of got confused over the lifespan of our typical apps, and that despite our best intentions, we always ended up in a bit of a mess. So we've emptied out our toolbox, and we've filled it with a collection of gems from 2 main projects, rom-rb and rom-rb. We use these together to form a functional, object-oriented approach to building web apps in Ruby. It looks pretty different from what we were doing previously. There's no more Rails way for us. This is alternative Ruby. And it's been pretty successful for us. We've shipped over 10 apps using this approach, including a large e-commerce website for an Australian publishing house. So at iceLab, we now consider this to be our default Ruby stack. So let's learn about these tools. How do we go and put together a rom-rb and rom-rb app? Well, firstly, if we take a step back and think about what a website is, I think we can reduce it to 2 things: getting data and showing it, and taking data and saving it. And because it's a website, the way we do that is to use the tools that HTTP makes available to us. So let's start there with a GET request. We're going to return some data, or get some data, and show it to the user. The starting point of a request like this is often a route. So let's begin there. We define routes using a routing tree structure. Here, we're defining a block for the products route. Then we describe what happens on a GET request. And we route to the view that matches the products index. This routing behavior is provided by a gem called Dry Web Rotor, which is our overarching app framework. It also allows us to define our HTTP entry points with Rotor, our routing tree toolkit. So in the context of our application setup, our route might look like this. Our app extends a Dry Web Rotor application, and we define our routes underneath. Next, we need a view. So let's look again at what that route is doing. We're rendering a view with a products index. To do this, we need another gem. It's called Dry View. It's a standalone view rendering system built around view controllers and templates. So let's go ahead and add a view controller for this view. Firstly, we inherit from Dry View Controller. We set up some config. Paths is an array of directories that will be searched for templates. Layout is the name of the layout to render templates within. Template is the name of the template for rendering this view. And then we add an exposure to make some products available to our view. Then we'd define a simple template, a layout matching that config, and output our products into the template. If we wanted to, we could extract common view config out into a shared base view controller class. Then we'd move our templates and layout config into the view controller superclass. Then our view controller becomes a bit simpler. We inherit from the app's view controller and only configure which template we're using. This is doing a little bit of setup for us. We use this pattern throughout the app. I'm only going to show you this once. But if you see superclasses, this is the kind of stuff it's doing. That exposure in our view controller is special. It's our way of declaring and preparing data for the view controller's template. And we need to add some real data to it by working with our app's dependencies. We're going to perform some dependency injection into our view controller, and it's made possible by a gem called Dry System, an object dependency management system. It depends on dry container for an inversion of control container and dry auto inject for simple dependency injection and resolution in our classes. So dry system makes an inversion of control container available to us throughout the whole app. And we can configure our container to automatically load our app's dependencies following a simple naming convention. And what that means is that we can use the container's import module to inject our dependencies automatically wherever we need them. So we can easily import a products repository so that we have access to that class throughout our view controller. Then we'd update our exposure to call a listing method on the products repository. And this method's responsible for retrieving our data for the view. So Dry System gives us pretty seamless access to this dependency, and we can use this pattern everywhere throughout our app. But if hearing the words IOC container and dependency injection are making you feel a little bit like this, try thinking of it simply as a hash where lots of objects are registered. You can look up objects by their name and use them, and the import module makes it easy to access them. It means you can compose your app logic with lots of focused, easy to understand objects, which is a real benefit. So next we need to build this repository. Here's where we're heading into the persistence layer of our app, which we get from ROM and ROM repository. ROM, or Ruby Object Mapper, is a persistence toolkit that's designed so that we have consistent, clear, and simple ways of interacting with our database, and so our app doesn't have to care about persistence details. Repositories are the bridge between the database and our app's domain logic. They control how we retrieve data as well as how we update it. And because the details of this might be specific to the kind of database that we're using, we use our repositories to define a domain-specific interface. So we make a repository class. The setup is inherited from our app's repository superclass. We have access to a products relation which maps to a particular database table. Then we add a listing method, setting a default limit. And then we retrieve products from the relation, order them, and apply the limit. Next, we need a database adapter for an SQL database. rom-SQL, another gem, provides this for us. There are lots of other flavors available. So we define a relation class. It maps directly to a table in our database with the SQL adapter, and we infer attributes, attribute names, and types. Then we define our API for reading data, our order by created at method, which returns the products ordered by their creation date. So then we have some data. Let's recap. We saw lots of gems interacting to make that GET request possible. It's the style of this kind of web app. There are lots of small gems, each with their own responsibility, all working together to make a cohesive architecture. Just like small objects, we work with small gems. It's a philosophy we use everywhere throughout this app. So, Dry Web Rotor gives us our app architecture and our routes. Dry System gives us an IOC container and easy dependency injection. Dry View gives us view controllers and the ability to easily control our templates. ROM repository gives us our persistence layer and the method by which we retrieve data from the database. And ROM SQL is our database adapter. And remember, we're responsible for defining how we retrieve data suitable for our domain in our repositories. So let's take a look at a post request. We want to accept some input, validate that it meets our expectations, and create a record from it. So we define post behavior for our products route. We have our products route block. We define a block describing what should happen on post behavior, and we're starting to see how a tree structure really suits routes well. The products route can contain behavior for both a GET and a post request. Next, we're going to resolve an operation from our container as part of the route. And the result of this will determine how we handle success or failure. Just a note, we're going to call the operation with the parentheses shorthand. So we add our operation to our route and pass in our form post data. Our operation will return an object that allows us to deal with success and failure within separate blocks. And when the result is successful, we might route to a success page. If the result is a failure, we might display an error page, or more realistically, we might redisplay the form with validation errors. And this is really nice, I think, because it treats the failure path with as much consideration as the happy path. So let's go a little bit deeper into what that operation actually looks like. The key here is that our operations have a consistent interface. Their only public method is call. One operation performs one action. So, how do we make it return that success or failure result? I have a surprise. We use monads. Well, we use two gems that give us monad-like behavior. They allow us to be really consistent about the objects our operations return, so we know how to handle them. And we kind of use monads in the way you might use a cookie cutter. You might be making biscuits of all different flavors, but if you use a cookie cutter, they'll all be the same shape. And here's what that looks like in practice. We define a create operation. We give it one public method, call. We import our products repository. Our call method passes the input to the create method on the products repository. And we return a write monad to indicate we successfully created our product. This pattern allows us to extend our call method to check whether the input is valid. And if it is, we return the happy path with a write monad. If it's not, we return a left monad with whatever we want to represent failure. And then in the failure case, back in our routes, our result becomes invalid input. To validate our input, we're going to use dry validation, which is a general purpose validation library that lets us define stateless predicates for our data, compose schemas based on those predicates, and guarantee the types we expect. Here's a simple schema for our products, which we'll add predicates to. The required predicate specifies that those attribute keys must be present in the input. Filled requires that they have non-nil values, and we're also specifying what types they should have. Stock levels value can be nil, but we're also specifying that if it has a value, it must be an integer greater than 1. Then we can call our schema with a hash of input. Again, that .call notation. And see that our stringy form keys have been coerced to symbols, the stringy date has been coerced to a Ruby date, and the empty string stock level has been coerced to nil. If we call our schema with invalid input, we get appropriate error messages back. And this makes dealing with form input really easy. Dry validation is enormously powerful, and you have the option to define your own error messages and your own predicates as you need them. Using our schema in our operation looks like this. We call the schema with our input. If the validation is successful, we create our product and return our write. If we have some errors, we return those in a left. This ensures we only ever create records with valid data. And now that we have some valid data, let's look again at how we create a record with it. We're calling a create command on our products repository. And again, we're heading into the persistence layer of our app through the repository. Defining a create command on a repository is pretty simple within the structure we already have in place. We define it using a commands macro. We can extend our CRUD operations really easily too, but we need to restrict those commands so that ROM knows which records to modify. ROM SQL automatically defines a by PK method, which restricts by primary key, so that's what we'll use here to restrict our commands. So here's what it would look like if we called the product's create command in isolation. Repositories return simple ROM struct objects, but the result of this is that a record will be inserted into the database. Then it's really easy to update a record by passing the primary key along with the data that's changing, which will give us an updated record. And if we want to delete it, we perform delete commands by passing in the primary key too. So let's recap. The core of our post request is an operation that handles validating and creating the product. Operations, we write all our operations in this style with one public call method so that the internals of the operation are encapsulated. We saw 3 new gems. Dry matcher and dry monads let us handle our operations consistently in our routes by returning rights or lefts and matching on that result. Dry validation lets us perform sophisticated validation on our input data so that we can handle invalid input before it gets anywhere near our database. And finally, we created some CRUD behavior in our repository with the create, update, and delete macros, allowing us to persist data into our database. And we have easy access to our repository in our operation. We palm off to it once we've validated our data. So, ta-da, we pretty much have a web app. Well, mostly. This is actually the real world, and this is real world Ruby. We need our apps to do a bit more. They aren't always simple get and post requests. We often have to perform actions on our data along the way. But this style of web app development has enabled us to do some pretty cool things with that. Remember that our operations have one public method, their call method. We use that pattern deliberately throughout our app. It lets us treat our app as a series of transformations on input data. Typically, we get an HTTP request on the way in, we perform a number of steps, and we get HTML out. The classes we're using to do this are still Ruby objects, but we write them in a way that means they behave more like functions. It makes them interchangeable and reusable. They separate their data from behavior. They don't keep input data anywhere in their state. But every time you provide the input, they behave in the same way. So I've got a bonus gem for you. It's a dry transaction, a gem that allows us to define a series of steps that make up a complex business transaction using our operations. It lets us define the steps on an abstract level without being coupled to any details about how the individual operations work. So a create product transaction might look like this. An operation to create the product. An operation to index it in our search instance. Then an operation to notify relevant users that a new product has been created. Any of these steps in the transaction can fail and stop the processing. But because all our operations return either a right or a left, the whole transaction returns either a right or a left. So we can replace the operation in our route with this transaction, and the success or failure is handled in exactly the same way. So if we could so easily swap out a single operation for a complex transaction, then I think we're really onto something. I think this hybrid between functional and object-oriented programming gives us lots of benefits. It also makes us think a lot more about app design. I was pretty new to Ruby when I started working with these libraries, and it's had a really big influence on me. I'm someone who works in the front end of apps a lot too, and it's really common for lots of logic to be in view templates. For front-end people who don't write a lot of Ruby, this can be a really confusing time. If it's not clear what the structure of your HTML will be, it can be pretty hard to build a complex JavaScript interaction on top. Drive view is super helpful here. It gives us really clear patterns for our view layer. It's enormously powerful beyond what we've seen today. And the end result is templates with minimal logic branching, which makes it easier to understand what output your template should give. The second thing I learned is that the database is a fundamental building block of an app like this. We are responsible for determining the relationships between data entities and how we retrieve data for the domain through our repositories. But our app is not our database, and design decisions we make in the latter shouldn't influence the former. It's important to have a clear boundary between the two. And loose coupling gets us so many benefits here. N+1 problems are not problems anymore. We get to name and specify each part of our repository API, which makes us think more about exactly what our app is doing or needs to do. But most importantly, if our app logic and our database are loosely coupled, we get to make good decisions for the business in both places. And I've come to realize that our apps now have really clear boundaries between each layer. Routing separate from views, which is separate from the operations, which is separate from the validation, which is separate from the repositories and the persistence layer. Each piece of logic in the app has a rightful place, which makes me feel good about our design decisions. It gives us the ability to understand what each piece of our app is doing. Nothing is hidden away from us. There is no magic. But we get so much flexibility because everything can work together. And it gives us the power to be better developers, to make the best choices that we can all the time. And it lets us do our jobs, which is to solve business problems for our clients. Haha, business. If you want to try it out, it's really easy to get started. Gem install dry rotor. There's a CLI interface where you can generate a new app. There are more resources on my GitHub Pages account if you want to read further into this approach. And there's also a dry web blog on GitHub, which we're building PR by PR, so you can follow along with a best practice app that follows these principles. I really hope you give this a shot for your next project. Thank you.